here by the lamp, in this quiet room where we've been sitting together these past few evenings. The light is the same as it was, soft, steady, the kind of light that doesn't strain the eyes, that lets you read for hours without noticing the time passing. The chair is familiar now, the weight of it, the way it holds you without demanding attention. This is our 5th evening with the missing 95%. 5 times we've returned to this room, to this lamp, to these pages spread out before us. There's a rhythm to it now, a pattern of return. We've been building something slowly, carefully, like arranging books on a shelf in the order they were meant to be read, each evening adding another volume, each conversation settling into the space the previous ones created. We noticed the blank pages in the universe's ledger. We confirmed something is written there. We looked at the candidates for what dark matter might be. Last time, we discovered that the pages themselves are expanding, that space is stretching, gently, across distances we can barely hold in mind. And we met the simplest explanation for that expansion: lambda, the cosmological constant, an idea with a century of history behind it, a placeholder name for the gentle push that seems to be woven into space itself, the same everywhere, the same strength through all of cosmic time. We left it there. Lambda on the shelf, a constant push. But tonight, we're going to open that question again, because there's something we didn't ask last time. We accepted that there's a push. We accepted that it seems steady. But we didn't ask whether it actually is steady, whether the strength of this push has always been the same, or whether it might be changing, not changing quickly, not changing in ways we'd notice in a human lifetime, or in 1,000 human lifetimes, but changing slowly, patiently, across billions of years, in ways that telescopes might be able to measure, if they're careful enough and patient enough. Back here by the lamp, that might sound like a small detail, a footnote, something that wouldn't change the main story. But it's not. If the push is truly constant, if lambda is exactly what the equations describe, then it's a fundamental property of space itself, woven into the fabric of the universe at the deepest level. Fixed, structural, part of the walls. But if the push is changing, even slightly, then it's something else, something dynamic, something that has a history, that evolves, that might surprise us. The pages we thought were settled might be shifting under gentle pressure we hadn't noticed. Not the words changing, not the ink lifting off the paper, but the paper itself, the medium, the substance, responding to something we haven't fully understood, adjusting its texture, its weight, its readiness to hold what's written on it. What does it feel like to realize that? To think the ground beneath the text might be moving, just barely, in ways you'd need very careful instruments to detect. Not unsettling exactly, more like curious. Like noticing the floorboards in an old house settle slightly with the seasons. The house is still solid, still safe, but it's responding to forces you hadn't been paying attention to. We can sit with that possibility for a moment before we ask how to test it. Here in the quiet, here where there's no hurry. This isn't just about refining a number. It's about understanding what kind of universe we're living in. If the push is constant, then we can predict the future with some confidence. The expansion will keep accelerating, gently, forever. galaxies will drift apart, the universe will grow quieter, emptier, cooler, over timescales we can barely name. The long rest. But if the push is changing, if it's growing stronger or weaker, or following some pattern we haven't seen yet, then the long-term story might be different. The ending might surprise us. And so, quietly, patiently, researchers have been asking, how would we even test this? How would we measure whether something as vast and subtle as dark energy is changing across cosmic time? That's what we're here to explore tonight. Not the answer. The answer isn't settled yet. But the question itself, the tools, what we're beginning to see, what the measurements are whispering. Here in our quiet room, we can turn the page gently and see what's written there. Let me offer you a way to hold this. Imagine you're standing in a hallway and you press your hand against the wall. You can feel the wall pressing back. That's positive pressure. The wall resists. It pushes against your hand with the same strength that your hand pushes against it. Now imagine the opposite. Not the absence of pressure, but pressure in reverse. Imagine the wall is somehow pulling your hand toward it, gently but persistently, as if the space between the wall and your hand wants to shrink. As if the wall has a kind of attraction, a draw rather than a push. That would be negative pressure. It would feel strange, unfamiliar. Your instincts wouldn't know what to make of it. You'd press forward, expecting resistance, and instead feel a kind of yielding, a gentle invitation inward. Not forceful, not grabbing, just a patient pull, like the way a soft blanket settles around your shoulders. This is the idea behind something called the equation of state parameter, which researchers label with the letter W. It's a way of describing how pressure and energy density relate to each other. A kind of ratio, a comparison. For ordinary matter, the matter we're made of, the matter in stars and planets, whiz positive. Matter pushes outward when you compress it. But for dark energy, for lambda, W equals -1. That's what a cosmological constant looks like. Negative pressure. A steady pull that doesn't change with time, doesn't dilute as space expands, just remains the same, everywhere, always. And here's the question researchers are asking. What if W isn't exactly -1? What if it's -1.1 or -0.9? What if it's changing over time? If W is exactly -1, then dark energy is lambda, a constant, a fixed property of space-time itself. But if W is anything else, even slightly different, then dark energy is something more dynamic, something that can evolve, something that has a shape we haven't fully traced yet. Back here in our quiet room, we can think of it this way. Lambda is like the walls themselves, fixed, structural, part of the house. You can't adjust them, they simply are. But if W is not -1, then dark energy is more like a presence in the room that can change. Not wildly, not quickly, but gradually, in response to conditions we don't yet understand. And if W is changing over cosmic time, if it was one value 10 billion years ago and a different value today, that tells us even more. It tells us the push isn't just variable in principle. It's actually evolving right now in ways we might be able to trace. We'll explore what that might mean later tonight. For now, let's let's stay with the question of how you'd measure it. Researchers have developed a way to parameterize this, to capture it in a form that telescopes can test. They use two numbers. The first, W0, describes the value of W today, right now, in our present epoch. The second, WA, describes how W has been changing over cosmic time. Think of it this way. W0 tells you how hard the walls are pressing right now, in this moment, in the room where we're sitting. WA tells you whether that pressure has been changing, whether it was stronger or weaker in the past, and by how much. If W sub A is 0, then W has been constant, no change, lambda. But if W sub A is not 0, then W has been evolving, and the size of W sub A tells you how fast. Two numbers. That's what the whole question reduces to. A snapshot and a trend. Where we are and how we got here. Back here by the lamp, we can hold those two numbers like coordinates on a map. W0 describes the walls right now, their texture, their solidity. WA describes their history, whether they've always been this way, or whether they've been settling, adjusting, responding to the weight they carry. And the deviations researchers are looking for are small, a few percent over billions of years, subtle shifts that require extraordinary precision to detect. So how would you measure whether W is changing? You'd need two things. First, you'd need very accurate measurements of cosmic distances, how far away galaxies are, and how fast they're moving away from us. And second, you'd need those measurements at different points in cosmic history, so you can compare the strength of the push in the early universe to the strength of the push today. Think of it like reading a book where the margins get wider as you turn the pages. If you only look at one page, you might not notice. But if you compare page 10 to page 100 to page 500, you can see the pattern emerging. The deviations might be only a few percent, like noticing the margins have widened by a fraction of a millimeter across 500 pages. You'd need to measure carefully. You'd need to be sure the change isn't just a printing variation, or a trick of the light, or the way you're holding the book. Researchers do this by measuring objects called Type 1a supernovae, stars reaching the end of their lives in a particular way that produces a known brightness. If you measure how dim they look from Earth, you can calculate how far away they are. And because light takes time to travel, looking at distant supernovae means looking back in time. By measuring supernovae at different distances, different moments in cosmic history, researchers can trace how the expansion rate has changed over billions of years. And from that, they can infer whether the push is constant or evolving. But there's another method, one that doesn't rely on supernovae. It uses something called baryon acoustic oscillations. Back in the very early universe, when everything was hot and dense, sound waves rippled through the plasma. These ripples left a subtle pattern in the way matter is distributed today. A characteristic scale, a particular distance, like a faint echo preserved in the arrangement of galaxies. Researchers can measure this pattern by mapping millions of galaxies and looking at how they cluster. The scale of the clustering acts like a ruler, a standard length, which lets them measure cosmic distances in a different way from supernovae. And one telescope in particular has been doing this work, quietly, patiently, night after night. A telescope in the Arizona desert, collecting light from millions of galaxies, building a map of the universe's expansion history with extraordinary care. Let's step into that room. The Dark Energy Spectroscopic Instrument, DESI, sits at the Kitt Peak National Observatory in Arizona, perched on a mountain under dark skies. It's attached to a telescope that was built decades ago, but the instrument itself is new, designed specifically for one purpose: to map the three-dimensional positions of millions of galaxies across cosmic time. It does this by measuring redshift, the stretching of light caused by cosmic expansion. The more stretched the light, the farther away the galaxy, and the further back in time we're seeing it. DESI can observe 5,000 galaxies at once. It has 5,000 tiny robotic positioners, each one moving independently, precisely, to point a fiber optic cable at a different galaxy. Each night, it collects light from thousands of galaxies. Each month, hundreds of thousands. Over the course of its survey, DESI is measuring more than 40 million galaxies and quasars, creating the most detailed three-dimensional map of the universe ever made. This is work that involves over 900 researchers from 70 institutions across the globe, astrophysicists, engineers, data scientists, people who design instruments, people who observe with them, people who analyze what the observations reveal. A collaboration that spans continents, languages, time zones, brought together by a single question. Back here by the lamp, we can think of it as turning millions of pages at once, each one a snapshot of the universe at a different moment, and arranging them in order so we can see how the story unfolds, how the margins change, how the spacing shifts. That's the kind of patience this work requires. Not the patience of waiting for something to happen, but the patience of careful measurement, repeated observation, methodical checking and cross-checking until you're sure what you're seeing is real. In April 2024, DESI released its first set of results. These came from the survey's first year, about 6 million galaxies and quasars, measured with care, their positions mapped, their distances calculated. And those results contained something unexpected. Not a conclusion, not a proof, but a hint. A whisper. The researchers had set out to measure whether lambda was exact, to confirm what most cosmologists expected, that dark energy is a cosmological constant, unchanging, fundamental. The goal was precision, refinement, narrowing the uncertainties. Instead, the data whispered something different. The measurements suggested that W might not be constant, that it might have been slightly different in the early universe than it is today, that the push might have a history. This was the kind of surprise that comes from careful, methodical work. Not dramatic, not sudden, just a detail in the data that didn't quite match expectations. A pattern that appeared in multiple ways of analyzing the results, quietly insistent. Back here by the lamp, we can feel the weight of that moment. The researchers checking their methods, running the analysis again, considering whether this could be a statistical fluctuation, a systematic error, or something real. The statistical significance was about 2.5 to 3 sigma, which in scientific terms means interesting, but not definitive. Researchers generally wait for 5 sigma before calling something a discovery, a standard that requires extraordinary evidence. So what DESI found was more like a detail noticed in the margin, something that might be meaningful or might be a trick of the light. But it was a whisper that appeared in multiple ways of analyzing the data. Different methods, different assumptions, and in each case, the hint pointed in the same direction. Here in our quiet room, we can set that page on the shelf. The 2024 result, the first hint, and we can turn to what came next. In March 2025, DESI released its second dataset. This one came from 3 years of observations, nearly 15 million redshifts, more than double the data from the first release. A larger volume of space, a wider range of cosmic time, more galaxies, more quasars, more careful measurements extending further back into the universe's history. More pages in the book, more carefully arranged. Think about what that means. 15 million individual measurements, each one requiring the telescope to point precisely, the fiber optic cable to capture light that's been traveling for billions of years, the spectrograph to analyze that light and measure how much it's been stretched. 15 million data points, each one a thread in a vast tapestry, and the hint strengthened. The evidence for evolving dark energy increased. Depending on how the data were analyzed, the statistical significance rose to between 2.8 and 4.2 sigma. Still not 5 sigma. Still not definitive, but closer, more consistent, harder to dismiss as statistical noise. One detail matters here. The DESI collaboration used what's called a blinded analysis. The researchers didn't see the actual results until after they'd finalized their methodology, their ways of measuring, their ways of testing for systematic errors. This is a discipline borrowed from particle physics, a way of ensuring that human expectations don't subtly shape the results. You decide how you'll analyze the data before you look at what the data say. You commit to your methods while the answer is still hidden. Only then do you remove the blindfold. It requires a particular kind of trust. Trust in the process. Trust in your colleagues. Trust that the methodology is sound enough to stand on its own, without needing adjustment based on what the results turn out to be. When they unblinded the data and saw what it showed, the evidence for evolution was still there. The measurements pointed, quietly but persistently, in the same direction. The collaboration noted, carefully, that the standard cosmological model might need modification. Not a declaration, not a claim of discovery, but an acknowledgement that something interesting is appearing in the data, and it's worth taking seriously. This is science at its most careful, not rushing to conclusions, not ignoring signals, but noting them honestly and continuing to watch, letting the evidence accumulate, letting the picture develop at the pace the universe allows. Back here by the lamp, we can pause and feel the weight of that. As of early 2026, DESI is still observing, still collecting light, still turning pages. The survey continues. So what is the hint saying? The data suggests that W was more negative in the past than it is today. In other words, the push may have been stronger billions of years ago, and it's been gradually weakening over cosmic time. Not quickly, not dramatically, but measurably, if the hint holds up. Another way to say it, the push may be getting gentler over time. Here in our quiet room, we can sit with that possibility for a moment. Not with alarm, not with excitement, just with curiosity. The universe might be settling into a different kind of acceleration than we thought. The expansion might have a more complex history than a simple constant push. What would it mean if that's true? We'll explore that question in a few minutes. For now, we can just notice it, hold it lightly, let it rest on the shelf alongside the other possibilities. This is still tentative. Many signals at 3 or 4 sigma have appeared in the history of cosmology and then faded when more data arrived. It's possible this one will too. The universe might be showing us a pattern that isn't really there, a detail in the margin that turns out to be a smudge. But it's also possible the pattern is real, that dark energy is not lambda, that the push has a history, a shape, an arc we're only now beginning to trace. The survey is planned to run for 5 years total. More data will come, more measurements, more careful analysis, and with each new release the picture will sharpen. The uncertainties will narrow. The whisper will either strengthen into a clear voice or fade into silence. Here in our quiet room, we don't need to decide tonight. We can let both possibilities rest on the shelf side by side. The instrument is watching. The question remains open. And that's enough for now. If W is changing, if dark energy is evolving over time, then it's not the cosmological constant. It's something else. The most common theoretical framework for this is called quintessence. The word itself is old, reaching back to Aristotle, who proposed that beyond the 4 elements, earth, water, air, fire, there was a 5th element, the quintessence that filled the heavens, the ether, the substance of the celestial realm. The ancients gave it a name because they sensed there must be something more, something beyond what they could touch or see or hold, a presence that filled the spaces between the stars, that held the cosmos together, that explained why the heavens moved the way they did. We're still learning whether they were onto something. Not the literal 5th element. That idea dissolved centuries ago. But the intuition that there might be a substance, a field, a presence filling space that we don't yet understand. Modern quintessence isn't the same idea, but it borrows the name. It refers to a family of theories based on the concept of a scalar field, a kind of energy that fills space. But unlike lambda, it can vary in strength. It can change over time or from place to place. Think of it this way. Lambda is like the walls of the house, fixed, structural, always the same. But a scalar field, quintessence, is more like temperature. It can be warmer in one room, cooler in another. It can shift as conditions change. It has a dynamic presence. There are many possible versions of quintessence, depending on how the field behaves. Some models, called thawing models, suggest the field was essentially frozen in the early universe and has only recently started to evolve. Others predict slow, steady changes over cosmic time. Still others predict oscillations or cycles. And here's the thing. None of these models were written down to explain DESI's hint. They were proposed decades ago as ways of thinking about what dark energy could be if it weren't lambda. DESI's data, the whisper it's hearing, is consistent with some of the thawing models, not proof, but alignment. A match between theory and observation that wasn't forced. Here by the lamp, quintessence is a possibility resting in the margin. Not the main text yet, not proven, just a candidate, written carefully, waiting to see if the evidence grows stronger. If W has been changing, that means the history of cosmic expansion is slightly different from what we thought, and it means the future might unfold in different ways. There are 3 broad possibilities. 3 pages we might turn to in the long run. First, if W is truly constant, if lambda is the answer, then the expansion will keep accelerating, gently, forever. Galaxies will drift apart. The universe will grow quieter, emptier, cooler, over timescales we can barely name. Imagine it. The stars burning out, one by one, over trillions of years. The galaxies fading, the distances between them growing so vast that light can no longer cross them. The universe becoming a collection of isolated islands, each one drifting alone in an ocean of expanding space. The long rest, the gradual evening, a settling into silence that has no end. Second, if W is weakening, if the push is getting gentler over time, then the acceleration might slow. Not soon, not in any time frame that would affect stars or galaxies or the stability of planetary systems, but far in the future, measured in many tens of billions of years, the acceleration might ease, and in principle, it could even reverse. The universe might eventually stop expanding and begin to draw inward again. Not collapse, not catastrophe, just a different kind of settling. Third, if W is strengthening, if the push is getting more intense, then the acceleration will intensify as well. This seems less likely based on current hints, and if it were happening quickly, it would lead to scenarios researchers sometimes call phantom energy. But we don't need to dwell on those. They're speculative, and the data aren't pointing that direction. Back here by the lamp, we can think of it as adjusting the angle of a bookshelf just slightly. If the shelf is perfectly level, books sit flat. But if it's tilted, even slightly, the books slide. Not fast, but over time the change becomes visible. The arrangement shifts. None of these possibilities require urgency. The timescales are so vast, they dwarf everything we know. Billions of years, trillions of years. Numbers so large they lose meaning, become abstract, settle into the realm of ideas rather than experiences. If W is changing, it's changing so slowly that nothing in our experience would feel different. The Earth would continue its orbit. The sun would continue to shine. The galaxies we can see would continue to be visible for timescales far longer than humanity has existed. What's changing, if anything, is our understanding. The room we're standing in is the same, but we're noticing details we hadn't seen before. The way light falls on the walls, the way the floor slopes just slightly, the way the pages turn. Let me add a few margin notes here. Ideas written in pencil, not ink. If dark energy is evolving, quintessence is one possibility, but there are others. Some researchers are exploring models where dark energy isn't a field at all, but a sign that general relativity, Einstein's theory of gravity, needs revision on cosmic scales. Modified gravity. The idea that the equations work well for planets and stars, but might need adjustment when applied to the entire universe. Others are considering coupled dark energy, models where dark energy and dark matter aren't entirely separate, but interact in subtle ways. Or early dark energy, the idea that there was a brief episode of extra push in the early universe that affected its development. These are speculative frameworks. Most of them will probably turn out to be wrong, but they're part of the process. You propose ideas, you test them against data, you see which ones survive and which ones fade. Margin notes. written in pencil, ready to be erased or promoted as the evidence develops. Here in our quiet room, we can leave these notes in the margins where they belong. Not the main text, just possibilities held lightly, waiting to see if the evidence strengthens or dissolves. DESI isn't the only telescope watching. In July 2023, the European Space Agency launched a satellite called Euclid, designed to map the shapes and positions of billions of galaxies from space, above the distortions of Earth's atmosphere. Euclid measures baryon acoustic oscillations, like DESI, but it also measures something called weak gravitational lensing, the subtle way dark matter and dark energy bend light as it travels across cosmic distances. Here's how that works. When light from a distant galaxy travels toward us, it passes through regions of space that contain dark matter. The dark matter's gravity bends the light just slightly, distorting the galaxy's shape. If you measure thousands or millions of galaxies, you can see the statistical pattern of these distortions. And from that pattern, you can infer how much dark matter is present, how it's distributed, and how dark energy is affecting the expansion. Euclid isn't just counting galaxies. It's measuring their shapes, looking for the faintest distortions caused by invisible mass. It's reading the same book DESI is reading, but paying attention to different details. If DESI measures the rooms, Euclid measures the furniture, the way objects are arranged, the way light falls on them. In March 2025, Euclid released its first results, data from about 26 million galaxies. The survey is about 14% complete. Full cosmology results are expected in 2026, when enough data have accumulated to make precise measurements. We may have new answers within a year, new constraints on W, new evidence for or against evolution. The picture sharpening. What Euclid will tell us is whether the patterns DESI is seeing appear in a completely different method. If they do, the case for evolving dark energy strengthens. If they don't, the question becomes more complicated, and researchers will need to understand why two different methods are giving different answers. Back here by the lamp, we can think of it as reading the same page in two different lights. Natural light from the window, lamplight from the desk. Sometimes the two illuminate different details. Sometimes they confirm what you thought you saw. Either way, you learn something. And there's another telescope coming. The Nancy Grace Roman Space Telescope, a NASA mission scheduled to launch around May 2027. Roman will observe from space, like Euclid, but with higher resolution and a different design. It will have a wider field of view than Hubble, allowing it to survey larger areas of sky in less time. And it will measure supernovae, weak lensing, and baryon acoustic oscillations. All three methods in a single instrument. Three ways of reading the same pages. Three independent approaches to the same question. Each one with its own strengths, its own systematic uncertainties, its own way of testing whether W is constant or evolving. By the late 2020s, we'll have DESI on the ground, Euclid in space, and Roman in space, all looking at the same question with different tools, different sensitivities, different systematic uncertainties. If all three see the same signal, the evidence becomes compelling. If they diverge, researchers will need to figure out why, and that process itself will teach us something about the methods, the assumptions, the subtleties we hadn't accounted for. Back here in our quiet room, we can rest with that image. Three telescopes, 3 methods, 3 windows opening onto the same landscape, each revealing details the others might miss. Here's what I want you to notice. This is an extraordinary moment in cosmology. Not because we have the answer, we don't, but because we have the tools to find it. Multiple telescopes, multiple methods, enough precision to measure changes of a few percent across billions of years. Think about what that means. For most of human history, the nature of the cosmos was a matter of speculation, philosophy, myth. Beautiful stories, some of them, but stories nonetheless. Then came telescopes. Then came the ability to measure, to test, to ask questions and have the universe answer, not in words, but in data, in patterns of light, in the positions of galaxies, in the way space itself is stretching. The Higgs boson took decades to find. Gravitational waves took a century from Einstein's prediction to their detection. Dark energy's nature might take time too. That's how science works. Not in sudden revelations, but in patient accumulation. Careful measurement, methodical testing. The universe reveals itself on its own schedule. Not when we demand answers, but when we've built the instruments sensitive enough to hear what it's saying. When we've learned to ask the right questions. When we've developed the patience to wait for the evidence to accumulate. And we have patience. The surveys take years. The analysis takes months. The process of checking, testing, reanalyzing, comparing. It's slow, careful work. Not dramatic, not urgent, just steady. If the text is changing, if dark energy is evolving, these instruments will see it. Not immediately, not all at once, but gradually, as the data accumulate, the picture will sharpen. The whisper will either strengthen into a voice or fade into silence. And if the text isn't changing, if lambda is constant, the uncertainties will shrink, and we'll be able to say, with confidence, that the push is exactly what Einstein described. Woven into space-time, unchanging. Either way, we're watching the question resolve. Here in our quiet room, we can feel the privilege of that, of being alive at the moment when the universe is revealing this particular detail, slowly, patiently, in its own time. The search continues, not with urgency, but with precision, not with anxiety, but with care. The telescopes watch, the data accumulate, the researchers analyze, check, cross-check, publish, and slowly the story clarifies. We began tonight by reopening a question we thought we'd already answered. We learned that dark energy might not be a constant. It might be changing slowly over billions of years in ways that telescopes are just beginning to measure. We learned about W, the parameter that describes how pressure and energy density relate, and how a value of -1 means constant lambda, while any other value means something dynamic. We learned about W0 and WA, the value today and the rate of change. We learned about DESI, the telescope in Arizona that's mapping millions of galaxies, and the hints it found in 2024 and 2025. Whispers in April from 6 million galaxies, then a stronger signal in March from nearly 15 million. Between 2.8 and 4.2 sigma, closer to discovery, but not there yet. And we looked ahead to the next few years, when Euclid and Roman will join the effort, when the picture will sharpen, when we'll know more. Let me step back for a moment and see where we are in the larger story. 5 evenings ago, we noticed the blank pages in the universe's ledger, the missing 95%, the matter and energy that don't shine. We confirmed something is written there. Dark matter, dark energy. 2 distinct presences, 2 different kinds of missing text. We looked at the candidates for what dark matter might be. WIMPs, axions, primordial black holes. Each one a possibility held lightly on the shelf. We discovered that the pages themselves are expanding, that space is stretching, that the universe is not static but unfolding, gently accelerating. And tonight, we explored what that expansion might mean, whether the push is constant or changing, what the telescopes are seeing, what the next few years might reveal. Next time, our last evening together this season, we'll step back and sit with the whole picture. We'll gather the pages we've turned and see how they fit together. We'll look at what we know, what we don't know, and what it means to live in a universe where most of the story is still being written. The book is still open. Next time, we'll close it softly. So where does this leave us tonight? It leaves us in a place of genuine uncertainty. Not confusion, not ignorance, but the kind of uncertainty that comes from standing at the edge of what's known, looking out at what's still being explored. The simplest explanation is still lambda, a cosmological constant woven into space-time, unchanging, fundamental. That explanation fits most of the data, and it requires the fewest assumptions. But there's a growing possibility that the simplest explanation isn't the right one. That dark energy is something more dynamic, more subtle, something that evolves as the universe ages. We don't know yet. The data aren't strong enough to decide, but we're closer than we've ever been to finding out. Back here by the lamp, I want to offer something that might sound strange. There's a comfort in not knowing yet, because not knowing means the question is still alive. It means the story hasn't closed. It means we're living in a moment when the universe is still revealing itself, still unfolding, still offering surprises. If we knew everything, the book would be finished. We'd just be rereading the same pages. But we don't. We're still in the middle chapters, and that means there's still discovery ahead. The universe isn't testing us. It's not withholding answers to frustrate us. It's just being what it is. Vast, ancient, patient, full of details we haven't noticed yet. And we get to be here, in this moment, watching as the details come into focus. Slowly, carefully, gently, so we can set this bookmark here. The equation of state parameter, W0 and WA. DESI's hints from 2024 and 2025. The question of whether dark energy is constant or evolving. The telescopes that are watching. The data that are still arriving. We don't need to hold it all at once. We don't need to solve it tonight. We can leave it on the shelf, resting quietly, while we turn our attention elsewhere. And when more data come in, when the picture sharpens, we'll return. We'll open the book again and see what's been written in the margins. For now, the lamp is low, the room is still. The pages are turning out there in the dark, at the pace the universe keeps. And here together, we can let it be.